Okay, so I'm going to make a start. So this week we're going to be talking about classes and class design. So over the last 2 weeks, we've looked at C++ and looked at all the stuff that's built in. We looked at the standard template library and all the stuff you can do with it. Now over the next 2 weeks, we're going to be looking at how do you go and build your own containers that you can then use within the standard template library or algorithms or other bits and pieces. And as you'll see up on the screens, assignment 2's been released today. It's due in 4 weeks' time. Okay? When you take a look at assignment 2, right now, when you take a look at assignment 2, you probably won't understand half of it. That's fine. The reason why I'm giving it to you now is over the next 2 weeks in particular, as we cover the material that assignment 2 then covers, you'll get the idea of how to do assignment 2. So the purpose of assignment 2 is to go out and build a Euclidean vector class. Now, a Euclidean vector is just a standard vector in mathematics, and is used normally in 3D graphics and things like that. You're building a class that provides functionality for vector mathematics, basically. Okay? Now, if you don't know what a vector is, you can go look up a textbook on linear algebra. I'd expect most people to know what vector is. The point I want to make is this isn't complex in terms of vector mathematics. It is a little bit complex in terms of C++, so it's quite a bit harder than the first assignment. But hopefully over the next 2 weeks you'll get enough off the lecture slides to be able to go and do this assignment. The other different thing about this assignment, and probably how you've done assignments in the past, is this assignment you're not writing a main function. You're writing a library. And so what you're going to be doing is you're going to be writing a .h file, a header file, and you're going to be writing a .cpp file. When we go and test this, I'm going to provide my own set of test cases which include a main function, and hash includes your .h file. And so the test cases is your code and my code need to work together. And if my code and your code work together, then you pass the test case. So there's a whole description of the capabilities and the functions that your class needs to provide. And again, some of these things like a move assignment operator and a destructor and stuff you might not know about at this point, but you will in the next 2 weeks. And so rather than a standard test case of here's some file you need to read, the test case is a .cpp file. And so the test case hash includes your Euclidean vector.h file. And here's a whole ton of things that your Euclidean vector should be able to do. And when we run this file, when we compile it and then run it, there is some output the same as what you've seen before. Okay? But this assignment is different to how you've probably done assignments in the past. Okay? But hopefully this should all make sense to you over the next couple of weeks. So take a look at that, not right now, take a look at that later on today or in the coming days. There's one thing I do need to make a note of is plagiarism. Probably everyone here has received an email in the last 2 weeks from the Vice Chancellor Education about a major plagiarism scandal that went on to do with people buying assignments. Okay, so here's the standard reminder. Do not copy code from internet, particularly C++ code, do not copy code from internet. Do not ask or pay someone else to do the assignment for you. This is an individual assignment, so do not work with other people on the assignment. And do not give your code to other people. Okay? And we run plagiarism detection software. And we, every semester, every class, every assignment, we pick up people for plagiarism. Okay? I don't like picking up people for plagiarism because it wastes my time, and please just don't do it yourself. Okay? So there's your reminder, don't plagiarize. If you have questions about assignment 2, again, use the course message board, send me emails, etc. Okay, the other thing I want to clear off real quickly is I had a question on Thursday after the class about hash define. And someone for assignment 1 had gone off and hash defined a whole ton of constants. Okay? Don't do that. Hash define is a pre-processor macro or pre-processor command that happens at the compilation stage. It's not part of C++, it's part of the compiler. Okay? It basically acts as a raw find and replace on your code. And so wherever you write the thing that you've hash defined, it acts as a raw substitution at that point. It's really good for header guards. Okay, so use hash define for header guards. That protects your code from being duplicated when you hash include the same file multiple times. okay? It's really bad for constants because you should be using const. And you might have learned how to do macros with it, and C++ use inline functions. The major problems of hash define is there's no type checking. Okay, there's no checking that this is actually the correct type, it's just a raw substitution. There's no scope, so we talk about namespaces, local scope, global scope. That doesn't apply with hash define. There's no memory address, the same as a variable declaration and definition. And put simply, it's not C++. Okay, so do not use hash define except for header guards. Okay, if you use hash define as defining a alternate constants or alternate macros, we will take marks off when it comes to assignment marking. Okay, so that is the explanation of why we don't use hash define. Okay, okay, so let's begin this week. We're looking at classes. We're looking at how we go and define classes. So we talk about object-based programming. Okay, so this, at this point still isn't strictly object-oriented programming. This is object-based programming. Okay, and so a class, okay, some sort of abstract data type that we build, uses what we call a data abstraction and encapsulation to define this data type. And it's split into a couple of components. We have for interface, okay, which are the operations used by the user. We might call this an API. There are a set of functions that your class provides that someone externally can use. For assignment 2, your .h file is defining some methods. If you scroll down this page here, here's your API. Here's your list of functions that this needs to publicly provide that someone else can go and use. Your implementation is what goes in the .cpp file. It's for data members. It's the bodies of the functions described in the interface, and any other functions that are not intended for general use. So you can include additional functions that are hidden from the rest of the programming thing. The implementation, so I said it went in the .cpp file. It generally goes in the .cpp file. Some of it will go in the .h file, and we'll see that again over the coming slides in the coming weeks. The idea of abstraction, it's separating the interface from the implementation. So we expose a public interface. We expose what we want to expose, okay? But for implementation, how underneath these constructors or these operators or these functions work is hidden away. The end user does not need to know that information. And we also talk about encapsulation. So the idea of information hiding, or the idea of bringing together some stuff, putting it inside a package. Like literally encapsulation comes from the idea of putting something inside a capsule. You're putting a whole ton of related stuff together, and you're closing it off as a package, and you're putting this entire package as one unit, one object. So the next couple of slides is going to be a whole lot of code. At this point, I don't care about you understanding this code. What you should understand is the ideas behind it. So we separate the code out into 3 components: the interface, the implementation, and the user code. So the user code uses the interface. And so in our .h file, okay, so we're going to be talking about this class called sales data. All this week we're going to be talking about this class called sales data. And it's a class that basically represents a bookstore, and each object in this class represents a book and the number of elements of this book that we've sold. Okay, so this might be the course textbook and we've sold 20 of those things. It might be a different course textbook and we've sold 10 of those things. And so in our .h file, which you can see here, we have the declaration of what this class is going to do. So we start up on line 1 and 2 with the header guards. Okay, so here are hash defines. Here are our preprocessor directives. We are defining the header file salesdata.h. It's got some includes like you've seen before, and then we go and say class, and class sales data. We then have some constructors, and again, the constructors are overloaded, so we've got multiple constructors. And here's some member functions. We have get book name, combine, average price. Again, they're declarations at this point. We're going to define them elsewhere. And then we have the declarations and, in a way, our definitions of what private data this class contains. Okay, so in this case, it contains a string. That should be an unsigned int, not just unsigned. A double about the amount of money we've saved, or amount of money we've made. And another unsigned int for the number of times this class or this method or something's been called. Ignore the word mutable for now. All of these things are setting us up for later on. Okay? So we have this interface at this point. The public part of this interface is we have three constructors, three overloaded constructors, and three methods. Okay? The end user cannot see this private data. And you guys should already all know this from when you've done object-oriented programming before. Okay? And at the end of our header file, just off the screen down bottom, is this end if. Again, it's a preprocessor directive to say we've defined this. Our definition, our salesdata.cpp file might look a bit like this. We hash include the .h file that we've created just on the slide above. And then we go and now define our member functions. And we can tell that we're defining our member functions based on this bit at the front of here, the sales data : bit. Again, it's the scoping. This is saying now this is a member function within the sales data class. And so here's the constructor. Here's a get book name definition. It returns a string. Note that this is const. We'll explain what the word const on the end of here means in a few slides' time. Well, actually, the short version, what the const there means, if you are paying attention right now, is the const at that point is not saying that the string it returns is const. What it is saying at this point is this method, this function, does not modify the class in any way. It's a const method, or it's a const member function. It does not modify the class. Now, everyone's going to scream at me and say, well, it says ++ number of times called. Again, we're going to come back to this in a few minutes. Okay? Same here, it doesn't modify it. Combine doesn't have const there because it actually does go and modify the class. So those there are member functions. They're defined inside salesdata.cpp and they're scoped to be within the sales data class. This next slide, these things are still inside salesdata.cpp, but they're considered non-member class-related functions. These are not part of the class. They might be part of the object that you're putting together, but they're not part of the class, even though they're related to the class. And so, again, we'll talk about friends probably in the second part of today's lecture, but these things, as this thing reads some data, and this thing prints some data. Okay, so these are functions called read and print, and they interact with the class in some way, but they're not part of the class. Okay. And then finally, we've got our user code. So this might be sales data user.cpp. And so this user code, again, hash includes our .h file. It doesn't hash include our .cpp file. Hash includes our .h file. It's got a main method that goes and creates, in this case, it goes and creates a Harry Potter book. And then it creates a new book with no name, and it reads some stuff from standard input. And it says, if the name of this new book and the name of the book we've already got is equal, then combine for data. Okay, so this is a pretty dumb example, but all this is doing is it's creating two books and seeing if the names are the same. If they're the same, then it's combining the data. Okay, you don't need to care about how that works. All you need to care about is the idea. So we've got the separation. We have for implementation, and then some code using that interface. And how we might compile this is very similar, or exactly the same as actually how we did for third-party library back in week 1. We create a salesdata.o file. The salesdata.o file relies on salesdata.cpp and salesdata.h. Okay, so this is where compiling our library. This is exactly what I'm going to do for assignment 2. This part is compiling the library that you've written. The second line of that is create the sales data user code, so the user code object. And so that's using the usercode.cpp file and again, your interface, your .h file. Okay, so now we've got two object files we've compiled, and then we link them together into a final executable. Okay, so it's a multi-step process. So people have got the idea of how we separate these things out into different object files and we link this all together? Everyone got that? Okay, so that's the high-level overview of what we're going to do over the next 2 weeks. Now, we're going to spend some time breaking it down. Oh, and again, one thing I should quickly make mention of is all this code is available. Okay, so I'm going to leave up on the right-hand side here some of the code, and we're going to talk through some of the code. And on these slides, we'll get little tidbits of it out. Okay. And this code here on this right-hand side is the completed code for this week. So whereabouts the individual tidbits over here might not compile. This should compile. It still doesn't do anything particularly exciting, but it shows you everything. So when we talk about a class defines a new type. Okay, a class is a type. It also defines a new a new scope. Okay, a class has a class scope. Okay, so the things that go inside that class are within a class scope. It's created using the keywords class or struct. Okay, so a struct and a class are essentially the same thing, but there are some minor differences. One of the key differences between a class and a struct is a class whose members are all public. Okay? When we're talking about object-based programming, that's okay. We can have a struct that's everything's public. Okay? When we're talking about object-oriented programming, then we're probably going to prefer classes where we've got things that are private. For your assignment, do a class, not a struct. Make sure you have things that are private. A class will define 0 or more type aliases, or types. It will have some data and some function members. It's possible to have a class that only has data and no functions. Okay, you probably want to make all that data public. It's also possible to have a class that doesn't store any data and it's just got a whole ton of helper functions in it. Might contain 0 or more public or private sections. Again, by default, a class has everything private, a struct has everything public, but you end up breaking it up into these sections of public and private. And it's instantiated through a constructor. So the object is created through a constructor. Okay, so that's a class. A member function, so a function that's inside that class, must be declared inside the class. So when the class is declared, the member function must be declared. So the declaration of the member function must go inside that .h file. It might or may be defined within that class declaration, okay, which makes it inline by default. So inside that .h file, we can define a member function, okay, or it can just be declared there and then defined in our .cpp file. And a member function might be declared as const. So I show you const before, okay, where it doesn't modify for data members. I'm going to put a giant asterisk next to that because we're going to come back to when it can modify for data members. But something that's const generally does not modify for data members. And the data members, generally speaking, should be private. They represent the state of an object. Okay? And you don't want things outside of your class modifying the state unless they explicitly request if a class does it. So that's why you have class member functions. They look after changing the internal state of a class. Okay? When I talk about state, can someone very quickly give me a definition of state? What does it mean when I talk about the state of something, particularly in terms of a class? This is something that people don't understand very well, at least from my experience of teaching before. If I ask you, define what it means to have the state of an object, what does it mean?
What values the data members have?
Yeah, it's what values the data members have. So the state of an object is not just of objects in memory. The state of an object is the exact values that each of those data members have at any one point in time. because then you have state changes, and state changes happen on the same object, and it's where the values inside a data member change. Okay? So we talk about a state of an object, and that can change over time. We talk about the state at a particular point. Okay? So it's really important to understand this idea of state. State is not just, oh, we have an object. State is, this is the exact values inside this exact object at this exact point in time. Okay? And your member functions help you to modify the state of an object. Okay, so we talked about encapsulation and abstraction before. Okay, but abstraction is formally separating the interface from the implementation. And encapsulation talks about hiding the details of how the internal class works. Okay? And the benefits of this is for object state. Okay, so we're coming back to this idea of state. For object state is protected from user level errors. That means that that user code, okay, so sales data user up here, it can't modify the internal state. So it protects you from someone else modifying your internal state and stuffing you up. Okay? And also it means that when class implementation evolves over time, hopefully, it's not guaranteed, but hopefully the user code that's already expecting to work on that public API will keep working even if the underlying implementation changes. Okay, keep on coming back to the idea of declarations and definitions, but a class is only defined once in a source file. If it's defined multiple times, the definitions must be identical. Okay? And so this is why you use header guards, to ensure that this happens, okay? Header guards guarantee that the code is only seen once. Now, it is possible to declare a class in the same way in which you might declare a function prototype or something like that. So you just say class foo, semicolon. Okay, that's called a forward declaration. You don't see this very often, but you see this when you have circular dependencies or circular class references. And you might get this in assignment 3, depending on your architecture. What that means is, say if I have, let's actually talk about assignment 3 maybe. Assignment 3 is a graph, okay? And a graph consists of a node and an edge, and the graph class itself. The graph class might need to know about the node class. The node class might need to know about the edge class. The edge class might also need to know about the node class. So you get the circular dependencies between nodes and edges. If it's not forward declared, your compiler just gets very confused and just keeps on going in an infinite loop. Okay? Well, actually it doesn't. It realizes something's wrong and it crashes. Okay? But so this forward declaration is really important when you have circular dependencies. When something depends on something, okay, so class A depends on class B, and class B also depends on class A. Okay? Now, with this forward declaration, we can also call this an incomplete type. Once we've got this class declaration at this point, we can define pointers and references to this class, okay? But we can't do other things with it. So this next slide, hopefully, here you go, looks at the idea of creating a class for a node or struct for a node. The first example up on that top of that slide doesn't work because you can't have a class within itself like that. So struct node cannot have a class object of node next and previous. Okay, it doesn't work because the class isn't completely defined at this point. But the bottom example does work because they're pointers. Okay? And that's about, so you need to remember that there's a difference between a base type and a pointer type. So in the top example, it doesn't work because the node type isn't completely defined at this point. The bottom example works because that node star is not a node, it's a pointer to a node. So a pointer to a node is its own different type. Okay? And again, we talk about the idea of public and private. And just, if you're coming from Java, everything you did in Java you had to say was public or private in front of it, or if you left it off, it became default. Okay? We have public and private with the semicolons, with the colons like this. And you put public there, colon, everything beyond that line until you say something else will be public. You say private, and everything beyond that line will be private. And can only be accessed by other members within that class, so it could be a public or private member, but it can only be accessed by other members in that class, and friends, and we'll get to friends in a minute. And this is how C++ supports encapsulation and information hiding. Okay? Hopefully a lot of this, if you haven't seen the syntax before, you'll already know the ideas from having done object-oriented programming. Okay. And finally, talking about class scope. Okay, so we've got a combine member function up there. You need to be very careful of how you read these things. This is a function called combine that returns a reference to a sales data object. It's within the sales data scope at that point there, this bit here. And it takes in a const sales data object. This scoping goes on the method name, not on the return type. Okay? You might need to put a particular scope on the return type, but that scope there needs to go on the member function. Okay? It's very easy to put that in the wrong place, or it's very easy to leave it out. If you leave it out, you get a compiler error that says, oh, I can't find this function, it's not declared. Okay? So you'll make that mistake, I make it all the time, okay? So be very aware of that class scoping. Okay. So we're all clear on classes up until this point. A lot of this should be revision at this point. Okay, who hasn't heard of the term this before? Like talking about the list pointer. Anyone hasn't heard that term before? Okay, so I'm going to assume people do. So within an object, you need a way of being able to talk about yourself. Okay? You do this through talking about this. Okay? It's implicit. Okay? It already exists. It exists for every class that you create. You don't have to create this yourself. Okay? And the compiler knows to treat this as a reference to yourself. Okay? So whenever you see the word this, the compiler knows how to interpret it. So if we look at this combine function again, what the compiler is really seeing at this point, what the compiler is really doing to your code, okay, if we go 2 slides back, see how this has only got one parameter at this point. The compiler is really doing this to your code. It's putting this extra parameter into your code. Okay? You're not doing this. Do not go write this bit of code into your program. Okay? It's implicit. It just happens automatically. But this is the point at which we start to talk about const. Okay? If we look on these next couple of lines here, we can have 2 sales data objects. Okay? 2 sales data objects. And we can call data 1. Okay, so sales data object number 1 dot combine data 2. Okay, and it's going to combine those 2 things. But if I have a const sales data object, okay, data 3, okay, so sales data 3 is now const, okay, means it can't be modified. So if I then try to say data 3 dot combine with data 1, which is non-const, it errors out because it's const, okay? Again, we can have a const member function like this. Okay, so get book name is const. It doesn't modify the internal state of the class. Again, it's conceptually defined as having a const reference passed into it. Okay. Now this can be invoked on a const object. Okay, so before previous slide, remember we couldn't call this .combine function because the method was const. So because the object was const. At this point, because this object's const and this method is const, we can call this get book name class. Book name member function. We can also call it on non-const objects. So sales data 2, data 2 dot get book name works fine. Okay, so this idea of const applies. We can have, at the object level, a normal object or a const object. A normal object, we can modify. We can change its state. Const object, once it's defined in memory, once it's declared and created in memory, you cannot modify it. In terms of member function access, a non-const object can access any member function provided it's public. A const object can only run const functions. Okay? So if we go back one slide, this combine class, so its combine member function, was not declared const because it modified the state. Therefore, because of that, a const object could not run this member function. On the next slide, this get book name member function is declared const, and because of that, a const object could call that method. Yep.
So if the combine function wasn't declared as const, and you had created a const object and tried to run it on, what would happen?
It wouldn't run. It would error message before you got to the compile stage. Okay. And again, you've got this code. You can go modify this code and see what happens with it. Okay. Now, the reason why I'm making such a strong point of this is when it comes to assignment 2, we talk about the idea of things being const correct. Okay? For assignment 2, I deliberately have not given you the .h file because I want you to figure out for yourself. The challenge that we're going to have with assignment 2, and so we're going to keep coming back to this, is this main method that I'm giving you, that is the test case, okay, is going to automatically assume that some things are const and some things aren't const. Okay? Now it's up to you to figure out what of those things are const and what of those things are not const. Okay, so that's part of a major trick of assignment 2. Okay, it's figuring out what things should be const and what things shouldn't be const. Okay, so we're going to spend quite a bit of time again over the next couple of weeks talking about when things should be const, when it shouldn't, what the meaning of the word const correct means. Okay? So, and again, for textbook and other resources go into a lot more detail on this sort of stuff. What we might find with assignment 2, to tell you the truth, we might find that people are very confused. If they are, we'll provide additional information about how to do it. Okay, let's talk about returning for object. Okay, so I have two member functions here. Okay, I'm just going to switch back to the source code here as well. I have two member functions. I have combine, which is not const. Okay, we're looking at this left-hand side. I have print, which is const. The first member function on the left-hand side returns a sales data reference. And a sales data reference is a reference to this. Okay, it's a reference to itself. So this combine object returns a reference to itself. This print function, actually this is not a member function, this is a non-member function, but it still works. This print function, oh no, I told lies. This print function is a member function. This is a different print function to what you saw on the previous slides earlier up. Okay, so I told you, on these slides there is some problems with compiling them. We're pointing out for issues to do with what you're trying to do here, not that this code will strictly compile. Okay, so this print function is slightly different to what you saw earlier. Okay, this print function is a member function. It is a const member function. It is also returning a sales data reference, but the reference it's returning is const as well. And so on line 4, we return star this. Oops. And on this slide 9 here, we say return star this. The return statement is the same, but the return type is different. The first one is returning a sales data reference. The second one is returning a const sales data reference. They are different. Okay? And so on this next slide, let's look at this next slide. Let's look at, I have sales data object A. It's got the name Harry Potter. Okay, and let's go find, actually, yeah, up on the side, let's go find the constructor for it. Okay, so the constructor for it is this top line here. Sales data reads on a const string, and it stores S, which is the string, in the book name. Okay, we'll worry about constructors in a few slides' time. Okay, but that's the constructor that's being called. On the left-hand side, that sales data A is calling the constructor on this right-hand screen, the very top constructor. Okay, so it's setting Harry Potter to be the name of a book. Sales data B creates a second object, also with the title Harry Potter. Okay. We then, on the left-hand side, say A.combine B. Okay, so maybe we've done some other stuff, and number A says that we have sold 3 copies of Harry Potter, and object B we've said we've sold 6 copies of Harry Potter. And so what we're saying is A.combine B, okay, so make 6 plus 3 is 9, and then print to stand it out. On the next line down, we're doing the same thing, but in a slightly different order. We're saying A.print, okay, so if A originally had 3 as being the number of elements sold, okay, and then we say .combine it with B, okay. Is there a problem in this code at any point? What I'm going to do is I'm going to flip back to the previous slide, and we're going to look at for return types. The return type for combine was a reference to the sales data object. The return type from print was a const reference to the sales data object. Okay, keep that in mind. One is const, one is not const. On the next line, we said A.combine, okay, so that returns a reference to the same object. Okay, because we've got that reference, we can call .print. When we say A.print, it's also returning a reference. But we can't say .combine because the reference it returned was const. Okay, so A and B were non-const objects. Okay, I need to be very clear about this. A and B were non-const objects. But because the .print, okay, I'm going to jump back, because the .print returned a const reference, it means that we can't call it .combine. Okay? Which is basically what this next slide's saying. Okay? So the ordering matters. Okay? Now we could have changed this and done this on some more lines, so we could have said A.print, semicolon, enter, A.combine B, that would have worked, okay? But this chaining, okay, this chaining of these things returning these references broke because one of the return references was const, okay? We've got 2 ways of solving this problem. Well, so you've got 3 ways of solving this problem. 1, don't have this problem in the first place, just by doing everything on a new line with semicolons, okay? Option 2 is we can overload based on const. Okay, so we spent a lot of time over the last 2 weeks talking about overloading. We're now going to talk about overloading based on const. And then we're going to talk about mutable data members. So, here are 2 function prototypes. They're both function prototypes for a print method. Okay? On the left-hand side, for return types are not what makes these things different. Okay, yes, the return types are different, but they're not what makes this overload work. It's the right-hand side that makes the overload work. It's the const at the end of here makes this thing work differently. Okay? And again, it comes back to a const object can only use the const member function. A non-const object can use either, but in general, the non-const version is a better match. Okay, so that's one solution to our problem. We just have 2 print methods, and the compiler works it out for us, and that previous code didn't work, now works. Okay? That might be one solution to your problem. The other solution that we've got is this idea of mutable data members. So I've been telling you for 3 weeks now that a const object can't be changed. And I showed you maybe in the second part of week 1 that, well, a const object can be changed if we cast away the const. Okay, and I said it was a dumb thing to do. Okay? You can do a similar thing here. It's not casting, okay, but we can have the idea of something being mutable. A mutable object or mutable value, okay, is something that even if the class is const, it can be modified. Okay? So when we talk about const, the computer doesn't care whether something's const or not const. Well, it does a little bit because it does do some optimization, okay? But the general reason why we use const, okay, is we're talking about the logical state of some objects or some code, okay? And it's designed to help you out. It's designed to help you not run into problems in your code, okay? So when we talk about const correctness, it's the logical state, not the physical state of an object, okay? So it's unusual. I've very rarely ever used mutable or even needed a reason to use mutable or even a const cast, okay? But in this case, say we have a function, it's called getBookName, and we wanted to count the number of times getBookName was called. Now, getBookName doesn't modify the class in any way, okay, so that's why it's const. But because we wanted to count the number of times this method was called, okay, so if class had some statistical reporting incorporated into it, okay, we might create a private class variable called number of times called, and we make it mutable. And because it's mutable, despite this thing being const, despite maybe that being called from a const object, that value can be modified. Okay? Who's confused about const yet? Anyone? A couple of people? Yep. Okay. You'll start to get the feel for this again as we keep going. Okay? So let's talk about constructors. So constructors define how we initialize a class, how we initially construct a class. Okay? And again, a lot of the first couple of bits of this should be revision. A constructor has exactly the same name as a class and no return type. Your constructor does not return void. Okay? People will try to do that. Your constructor does not return anything, it's got no return type. Okay? Default initializations handle through a default constructor. What that means is if you don't create any constructor yourself, you get a default one. If you do create a constructor, you don't get a default one as well. Okay? And we talk about, and we're going to go into detail with the next few slides, the synthesized default constructor. What the compiler automatically generates for us. So this is what it looks like. The default constructor, and the logic of how the code works, does this. For each data member that we've declared, okay, so I'm going to, on the right-hand side, look at this ordering of our declarations, okay? Our class here has a string, an unsigned, or an unsigned int, if you want to be pedantic, a double, another unsigned int, and another int, okay? So there's a particular order to how that's happened, okay? For each data member in that order, if it has an in-class initializer, okay? So if it already has a constructor for that particular data type, so say string up here, okay, that has a constructor, initialize it using an in-class initializer. Else, if it doesn't. If it's a built-in type, it's undefined. This int down here, this counter, the value of this at this point is undefined. It's not 0. It might be 0, depending on your compiler, but it's undefined. Okay? If there was a different class at this point, okay, and if the other class didn't have a default constructor, so it didn't have a custom constructor, it will be initialized using the default constructor. Okay? But you can run into problems like this, okay? So you shouldn't rely on the default constructor. You should basically always define your own ones. The reason why you shouldn't rely on this. Consider we have a class A, and class A defines its own constructor to not do anything. Class B doesn't have a default constructor. Doesn't have any constructor. So it gets one synthesized for it. Okay? Has the value I set to 1, okay, using what's called an in-class initializer, that's fine. Int J is undefined. Okay? A here, just A like this, works at this point, okay, but doesn't work if this class A over here had a different type of constructor, so say something that took an int. Okay? So you've got to be very careful at this point. Okay? This is why you should always define your own constructors. Okay? Because otherwise you might have problems that you don't expect. Okay? So the default constructor, the synthesized default constructor, is generated if you don't declare your own one. Is incorrect if some of the built-in types have no in-class initializers. Is unlikely to be correct if some members are pointers, particularly raw pointers. Okay, and this will, when we look at copy control, which is Thursday and next week, this will become more clear. And can't be generated for a member of a user-defined type if the type doesn't have a default constructor. Okay, so as previous slide, if we modified A to not be of that form anymore, but to take in an argument like an int, then this won't compile. Okay. So how do we define a constructor? Can I get a feeling who's programmed constructors before? It doesn't have to be C++, but who's programmed constructors before? And what languages have you used? Java? What else have you used? Python? Yep, what else have you used? C#? Okay, I don't know enough about C#, okay, but I know a bit about Python, a bit about Java. When you've created a constructor in Java or Python, what you would have done is you would have had a class and given it the class name, given it some arguments, and opened up some braces. Okay, and you would define some stuff inside there. If you're in Java as well, you might have used a very similar thing to the in-class initializers. Okay? The extra bit that we've got here in C++ is this constructor initializer list. This runs before the braces to do the rest of the constructor. And as we'll see in a few slides' time, even if you define something else or set a value within those braces, what happens is this first bit here, even if you don't write it, gets substituted in. And so stuff might get default initialized before you override it. So your constructors should always, where possible, use the initializer list, not what goes on inside that bracing. Okay? So if you're coming from Java or Python, I don't know about C#, okay, but if you're coming from Java or Python, be very aware that this constructor setup is different. Okay? And so that's what you see up here. Okay, I'm going to highlight line 9 again up on this right-hand side. This book name is what the initializer this looks like. Okay? So we haven't gone inside that bracing and said book name equals S. That book name is the initializer list component. Okay? So it happens before the constructor or the body of constructor runs, and it happens regardless of whether you make it happen or not. Okay? And the constructor will initialize all the data members. Okay? And each data member, as you saw on the previous slide, is initialized using the constructor initializer or the default value, and using the same rules that we saw above. Once it's done that, then the body of the constructor is executed, which might assign values, okay, and override initial values, okay? So it's really important to do this initializer list, okay? On this next line down up here, so 10 and 11, let's take a look at this in more detail, okay? Line 10, we've said we've got a constructor sales data. It takes in a string, it takes in an unsigned int n, and it takes in a double p, colon. book name S, comma, units sold N, comma, revenue P times N. Okay, so we can do some math in there. Then the main part of the constructor, where you might have done that stuff before, is empty. Okay, so if you're coming from Java, if you're coming from Python, this is very much a different way of doing it. Okay? Line 12 we'll talk about in a few minutes, because this is a different way, again, of doing this. Okay, so let's talk about overloaded constructors. Okay, so like I just pointed out, that's what the constructor initialized list looks like. Okay, and like I just explained, those data members are initialized, and then the empty body is executed. This next bit, so explicitly initialized book number, is actually old text. Okay, so that's not in the code that we've got here. Okay, but what we're looking at, or the explanation of what's going on there, and you see this top one. You see how we didn't initialize units sold or revenue in this top one? Okay? That just default initialized. Okay? So that's the equivalent of doing, if we look on the left-hand side over here, units sold 0, revenue 0. Okay? So that top constructor, where we didn't supply the values for units sold and revenue, gets default initialized to 0 like that. Okay? And the third way of doing constructors is still to do your old-fashioned style, that if you've done Java or if you've done Python, it will look like, okay? But, as I point out, due to the lack of initialized lists, so your custom initialized list at that point, they're going to be initialized, like you saw before the body of this constructor is called. Okay, and that can cause problems, as we're about to see. If we have some members that are const, or references, or have no default constructor, they have to be defined on the initializer list. You can't write a function or constructor that looks like this. No initializer list, go into a body. Okay, first line works because it was uninitialized. Okay, so int I, okay, works here, passing an II, that's fine. CI, which is a constant, can't be assigned because it's already been initialized before you got to this line. Okay, so this const int CI was fine to be initialized at that point up here. Down here it's not. RI, so our reference, our int reference, cannot be initialized here, has to be initialized on the initializer list. Okay? And our thing with no default constructor doesn't exist. Okay, so this bottom constructor just will not work. It's full of problems. Okay, even though that bottom constructor looks very similar to what you would have done in Java before. Okay, so be aware of that. Order is also very, very, very important. Here's a class. It's got I and J. If our constructor tries to construct J first and then I second, it doesn't work as you expect it to work. Has to be done in the order in which it's declared down here. Okay? So in this case, if you wanted I and J to be the same value, you can either say I is val being passed in, J is being val being passed in, or I is equal to val, J is equal to I. You can do that. This top one does not work. Also note when we talk about destructors, okay, destructors work in the opposite order. Okay, so we'll talk about destructors, I think on Thursday. Destructors work in the exact opposite order to constructors. So the destructor for this would destruct J before it destructs I. Okay. Now, the next extra piece of this in C++11 called a delegating constructor. Now, I've given you a hint in the assignment, you might want to use one of these things. A delegating constructor is a constructor that might do some stuff, but then call a different constructor. line number 12 up here is exactly this. The default constructor that we've declared for sales data actually is a delegating constructor to the constructor defined on the line above, whereabouts we're passing in those default values. Okay? So a delegating constructor is a constructor that's able to call another constructor. Okay? So here's an example of how to do it. I've recommended you do it for one of the constructors in the assignment 2. Okay? It just basically saves on some code. If you've got 20 constructors and they all do very similar things, but they've got slightly different arguments, you can figure out what your base one is and have all the other ones delegate through to there. Okay? At this point, I'm going to stop for 5 minutes and let you guys, process all this. Okay, so we'll pick back up in 5 minutes' time. Okay, so let's resume. Okay, so what we've done is we talked about how to build a class. Okay, we talked about member functions, we talked about data members, and we talked about how to construct objects. Okay. What we're now going to spend for the second part of today talking about is friends, which are not member functions, but they're functions that are class related that can interact with our class. We're going to talk about casting in the terms of how we make our class able to be casted, and we're going to talk a bit more about scope. Okay. So friends are not members of a class. Okay, but a friend can be a member it can be a function, or some other class, or some other class's member function that we declare as being able to access any part of a class's piece of private data or public data. Okay, so they're not affected by access control. A friend member function, or friend class, or friend member function can completely access all the private data of our class. Friends and friend declarations are part of a class's interface. So if we go to the .h file for sales data, we will see that we have these friend declarations inside the class declaration. Okay? Friendship is not transitive, reciprocal, or inherited. What that means is I have class A and I say class A allows class B to be a friend of class A. It does not mean that class B, sorry, it does not mean that class A is then a friend of class B. It works in one direction only. Okay, so if class A declares that class B is a friend, class B can access all the private data of class A, but class A cannot access all the data members of class B. Okay, so I don't declare that you are my friend. Okay, I don't declare you're my friend, I can access all your private data. I declare that you're my friend, and then you can access all my data in that direction. Okay, and it's also not inherited. We're not going to talk about inheritance until about week 10. Okay, but this is something to store away until week 10. Friendship is not inherited. Okay. Friendship is often used for operator overloading. Okay, and again, we'll look at this a lot in detail next week. But what this means is, say our sales data class here, okay, we create an object. We might want to be able to push the sales data object, the whole object, out to cout. Okay? That's exactly what we want, and we want to do that in assignment 2. But we don't want all of cout being redirected into sales data. That doesn't make sense. Okay? So friendship is often used for those things. Okay? We can also define some non-member functions that can modify. I don't know why it's saying don't modify. Okay, but we can define a class called add. Oh, I know what it's doing. We define a class called add. So member function add. So start again. We define a function add. Okay, it's a non-member function. It's a non-class function. It takes in a sales data object here. It takes in a second sales data object here. It's going to add those two things together and return a third sales data object. Okay? So here's the interface. Okay, I've shown you this up on the right-hand screen already. We have the friend declarations inside the class. We also need for declarations outside of class. Okay? The friend declarations declare this thing's a friend. It doesn't declare that that function has also been declared. Okay? So there's a separation between a friend declaration and a function declaration. Okay? So you need both. And that's what you'll see here. Friend declaration here, function declaration there. Okay? So there's three types of friends. There's an ordinary function. Okay? So print, okay, might be a friend. Okay, so the print that I showed you before wasn't, it was a member function, okay, but in this case, this print is a friend function. We might have a whole friend class. We might have a class called screen, and there's a window manager, and so window manager is a friend of screen. Window manager can access all of screen's internal data. Screen cannot access all of window manager's internal data. And you might have a member function of a class being a friend. Okay, it's infrequently used, but say we've got another screen class. This particular relocate function inside window manager may be a friend. Okay? Again, this is up on the declaration level. Okay? Remember, friends allow access to all data. Now, there is a difference between friendship declarations and type declarations. Okay? We've got x.h. It declares a friend class y, and it declares a friend function which actually declared inline, okay, to do nothing. This first function inside user.cpp works fine because it's declared inline. But it doesn't, well, actually, it doesn't work because f's not declared in scope. Okay? And also y is not declared in scope. So this .h file here, class y, even though it's declared as a friend, class y was actually never declared or defined anywhere. Okay? F wasn't declared inside the scope. Okay? So we still need to have those class and function declarations down there, and then it works fine. Okay, so that's the point I'm trying to make. Okay, so a friend declaration only specifies access or relationship. Okay, it doesn't declare these things in memory. Okay, things that aren't friends and aren't function members or class members cannot access the private members of a class. Okay, but you might still package them in the same set of libraries. Okay, so in this case, it's line 38, so right at the bottom of this .h file here. I have a function called add that returns a sales data object. This is not a member function of sales data. It is not a friend of sales data. It can only access the public exposed interface of sales data because of that. Okay? And so what we might want is sales data D1, sales data D2, so these two things. Call this add on D1, D2, and produce a third D3 at this point. Okay, because we don't want D1 and D2 to be modified. This add, you might also want to put the word, like I've done in my example, const in front of that. Okay, specify you do not want to modify these things. Okay? Okay, let's talk about type conversions. So we've already seen that we can overload functions. Okay, we're going to keep coming back to some of these points. We've already seen that we can overload functions. So here's a screen class. Okay, it has two functions called set. Okay, they're overloaded based on the differences in their parameters. It has two functions called display. They are overloaded based on whether they're const or not const. Okay? So that's some normal ways in which we can overload some stuff. Okay? And they work with different types as well, because remember, const is a specifier. So one of these will work with a const version of screen, and one of them will work for non-const version. So let's look at how these things work. For non-const screen object, goes and creates this object. It calls the non-const version of display, okay, and might say print this thing out to the console. And the non-const version might say move to this position and set this particular thing, okay, and that works because these things are all non-const. So we saw this in the first hour. This const screen object calls the const version of display with the console out. But then when it tries to move and tries to set it, you get an error. And we saw this in the first hour. Okay. Let's talk about static data members. Okay. In our class, we have a thing called counter. Okay. So on line 29. We have this thing called a static int called counter. Something that's static, okay, exists across all instances of a class. Okay, it's one version of it across all instances of the class. Okay? It is part of a class, it is not part of an object. Okay? So an object is a class instantiated in memory. A static data member is part of a class, not part of an object. Okay? Objects only contain non-static data members. Okay? So in our header file with a static counter, we declare it there. We define it in our .cpp file. If I can find it, there it is down bottom. We define it completely outside of any constructor. A static data member does not get initialized inside a constructor. Just gets initialized just right there in that piece of code. Okay? Static data members are rarely used, but they are used when, again, you might want something that's const and constant, by that, what I mean by that, across all classes. Okay? So you particularly might use some sort of static thing if you had a version number. Okay? The static members, okay, despite this being inside a private area here, can just be accessed anywhere in the user code. And they're accessed not strictly by the names, okay? They can be accessed by the class name or they can be accessed by an object name, depending on if you want to resolve them that way or you want to resolve them that way, okay? Both those lines of code work. Okay? Often with static members, you resolve them through the class name, not through a variable type object name. Okay? So let's talk about type conversions. So constructors are used to create types from other types. They bring together a whole ton of data. Okay? So a constructor makes some implicit conversions from one type to some other class type. And that makes sense because constructors build stuff. Okay? Now, what we can do with constructors is some quite interesting things. We here have a class foo. It has a constructor to take in a vector, initializes this to copy that vector into the data member there. Okay? And so we can say create as a vector, okay? But instead of saying foo equals brackets ivec and call that constructor like that, foo equals ivec. Class foo is equal to a vector. Got someone over there screwing up their face at this code. Okay? Yeah, look at you. Yep. You can do this. You can do this because it gets implicitly converted across. Okay, I wouldn't probably promote doing this because it is confusing when you first glance at it. Okay, but there's a type conversion going on there that C++ implicitly allows you to do. Yep.
That doesn't throw any warnings or...
No warnings. You're allowed to do this. Okay. Didn't say you should do it, but you can do it. Okay. C++ lets you do a whole ton of wonderful, amazing things that you probably shouldn't do. Okay? So what we've got here is foo is being constructed and defined at this point. This constructor is automatically being called. Okay? Now, only one type conversion is allowed. What that means, okay, you guys who are screwing your face up, you're going to hate the next couple of slides, okay? Only one type conversion is allowed, okay? So we have a string here, gets given value 123, and we've called that variable nullBook, okay? What we can do is we can create a sales data object called data1, make that have for string 123 and value 1 and value 20 go in, okay? And this is using the constructor we saw earlier on in the day, so we just find it, there it is. So this constructor on line 10 and 11 of salesdata.h is being called on line 3 of this code on the left-hand side. We can say data1 dot combine nullBook, because nullBook is a string. Even though that dot combine is not taking in a string, that dot combine, which is down here on line 17, is taking in a const sales data object. This works. You horrified yet? Okay? You're surprised. That's because what that code is implicitly doing is it's creating a second data, sales data object in memory through that constructor. So we've got a constructor up here, it just takes in a string. Okay, so this constructor on line 9 is implicitly being called. We haven't told it to, it's just implicitly happening. Okay, it's creating a second object in memory and combining it. Okay? You look absolutely horrified up there. And then we can call print. Okay, print to see out that data. Okay, I don't know what that endl is doing on the end of there, but we can print that out, and it works. Okay? So one type conversion is allowed. We have constructor that allows that conversion from the string to the sales data object. So even though we didn't create that object, it just implicitly happens. But the good news is you can't do it twice. Okay? The good news is you can't do it twice. So convert 123 to a const char 4. Okay? So 123 just like that is a const char. Okay? One of these things that we had back in C land. Okay? If we want to convert that to a string and then convert the string to a sales data object, it doesn't work. Okay? So again, we create data1. If we just said data1.combine 123 like that, it doesn't work. Okay? So the top one of those things worked, the next one down doesn't. The next line, I really hope no one ever does this, does work, and it's absolutely terribly confusing. The next one again goes and creates us one sales data object. We then say sales data1 dot combine standard cin, passing the whole keyboard into it. Okay? The reason that works is we have a constructor that takes an input file stream. Okay? So that constructor is being, at that point, implicitly called, and it works. Okay? Don't do this. Don't do this, but be aware that these things happen. These things are allowed. Okay? But there's good news, you can stop it from happening. Okay, so here's the good news, you can stop it from happening, because it can be dangerous. If we put the word explicit in front of a constructor, okay? So I haven't done it here, let's do it here. If I put the word explicit, did I spell it correctly? Yep. In front of some of these constructors, okay? That means that it has to take in exactly what has been given. Okay? So it doesn't allow that type conversion to happen. Okay? Yep.
Does that affect whether you can take in a non-const if you set const?
No, it shouldn't affect const. It's affecting that type conversion. Okay? It should not affect const. But again, code it up yourself, double check that. Okay? So, now, let's go back to that first example. We've made that thing explicit. Now when we try to, say, combine null book, it doesn't work. But this does work. Combine sales data, null book. Okay, so now we've explicitly called the constructor for sales data. Okay, again, if you're coming from Java land, be aware there's no word new in front of that. Okay, we can do this just like this, perfectly fine. Okay, and now that works fine. We've explicitly expressed what we're trying to do. Okay. And the same thing works on these lines down here. Whereabouts before the standard cin worked, now it doesn't because we've got to explicitly say we want to read from the keyboard into a new sales data object and do it. It also works if we do a static cast. Okay? So if we do a static cast, it will figure out how to convert the standard cin into a sales data object and then into the combine. Okay? So we've got implicit and explicit type conversions. Okay? And again, in the coming weeks, we're going to talk about how you write your own type conversions. Because again, part of the brief for the second assignment is can you convert your Euclidean vector into a standard vector or into a standard list. Okay? So you need to allow, okay, you'll learn how to do this, how to convert your class into a different class. Okay? So last week we looked at the vector class in detail. And we looked at all the different constructors that they had. And one of the constructors that they had was a constructor that took the size that the vector should be. Okay? So on line 5 of this code on the left-hand side, we're creating constructor vector v with size 10. Okay? That's okay. But we can't say standard vector v equals 10 because the vector's size constructor like that is explicit, okay? So that explicit prevents that from happening, okay? Say we had void f here, and void f took in a standard vector, okay? We can't say f10 like we had before because it's explicit, okay? But we can manually construct it, okay? So some things in the standard template library are implicit and some things are explicit, okay? I have not, honestly, off the top of my head, thought about which ones of these constructors for assignment 2 should be explicit or not. I might actually work on that and might come back with you guys on if I expect that at all, okay? Generally, I do not like the idea of things not being explicit because, as you've seen, it can lead to some very confusing code, okay? Okay, so let's talk briefly about class scope. Okay? So, when we've talked about declarations and definitions so far, we've always said that things need to be declared before you can call them. Okay? With classes, that works a little bit differently. Okay? So there's 2 steps involved in finding the declaration of a name. Okay? First of all, consider what you've seen earlier. Okay? So C++ generally goes from top down. Okay? But then it might also consider what else is in the class's scope. Okay? There's then three names for looking inside and outside of the scope. Consider what's happened before, consider the rest of the stuff in the class, and then consider what's inside that particular scope. what that means is I can do things like this. Type def, double money. Okay, we haven't talked too much about type defs, but type defs are basically just aliases. We're creating an alias for type double, calling it money. Okay? We then have a string balance. Okay, I don't know why it's a string, but anyway we do. We then have a class account. We then say money. Okay, that's just for substitution for double. Yeah. Okay, so that goes and looks for, okay, do I have a class called money? Do I have some sort of other declaration of a thing called money? Nope, I'm going to go all the way up here and find this type def for money. Okay? This return bow at this point, even though bow being of type money is not declared until after that return type. Okay, normally in C this would spit an error at this point. Okay, but C++ is slightly different. This here, this return bow is not in local scope. Local scope is between those two braces there. Bow is not in local scope. I have a bow sitting inside the class scope. I also have a bow sitting inside the global scope. Even though the class scope version is declared after that return bow, this works. It finds the class scope. Okay, so it kind of works local scope, class scope, global scope. Okay, when finding name resolution, this is in class scope only. Okay.
Does types have anything to do with this? So, like, say for argument's sake, you had the private field in there be a type string, and the one outside the class be.
No, so it's got nothing to do with the type. It's to do with the name. It's the name resolution. Okay. So I don't know why that's a string. Okay. I've inherited some of these slides. Okay. That's my excuse. It's going to be my excuse all semester. If there's an error on the slides, it's not my fault. It's who I inherited them off. Hopefully I can use that. But it's got nothing to do with the type at that point.
So if they were swapped,
Okay.
you'd still get those.
Yeah, it should do. I'd expect it to. And probably, in that case, it would get it, and then it would go, this doesn't make any sense because I can't figure out how to convert a string to a double. Okay? But it should still get that point. Okay, again, maybe code this up, figure it out, work it out. Okay? If it does something different, tell me, we can work it out. Okay, let's look at this one. We have a function foo, declared to do nothing. We have a type def of an int. Okay, so we've got an alias for an int. We're just going to call it a value type. Okay. We then say class foo has foo1 return int. Okay, that's fine because it's in different scopes. So we've now got two foo functions. Okay, and that works because they're in a different scope. Okay, it's got nothing to do with return types at this point. Okay, in fact, we've got foo1 being void and foo1 being value type. That's got nothing to do with any problem we're going to have here. The redefinition is perfectly valid because it's in a different scope. However, if we now try to redefine value type to now be a substitute for word double, it doesn't work. Okay? Because this name at this point is being used. Okay? Once it's been used as a type, so this is type defing. Once it's been used as a type, it can't be redefined. This version does work. Create a function for foo1. Create a type def value type. Okay, it's substituting for int. We'll go inside the class. We now type def value type to be double. The redefinition works because we haven't used a value type at this point. So on the next line, value type foo1 works perfectly fine. Okay, again, this is name resolution. Okay, so again, this ordering matters. This type def hasn't been used, so you can redefine it. Once it's been used, it goes, nope, I've been defined, I can't be changed. Okay, so names in the class member function are resolved by, again, local scope, class scope, and then looking what's happened before that in the outer scope. Okay? So this one hopefully should be easy, but here's a quiz for you. We have int x equals 1. Okay, we've got int x equals 1. we have a struct or class foo has a member int x. We then have a constructor of a foo make the value of x inside foo be equal to 2. Okay, so we've got an x which is equal to 1, we've now got an x that's equal to 2. We then have a print function. It takes in a reference to something that's also called x, and then we're saying print out x. So there's 3 x's in this program. Okay? We create foo f, and we say f print 3. What is going to be printed out? 1, 2, or 3? Who thinks 1's going to be printed out? Anybody? Who thinks 2's going to be printed out? Who thinks 3's going to be printed out? Most people think 3's going to be printed out. It's not there. It is 3, okay, because the local scope happens first. Okay? Again, don't write code like this. Okay? Let's talk about G here. Okay, so here's a function. Okay? We again have foo, and it does some printing of x. We then have this function G, it returns 3. Okay? We then have the definition of this member function. So, okay, so print was declared here. We then define it at this point. Okay, it's no longer a reference, now a copy, okay? And it prints out G. And it calls G at this point. So G here, it returns 3. So this is just going to print 3. Okay? But look at this very carefully. Our main function, f.print G. Okay, so the G up here gets called, passes in 3 into there, it gets copied, but that's not X anymore, that's G. Okay, so that's why it works like that. On this next slide, this is going to change. I have a static function, static int G, return 4. Because this is now within class scope, this G is masked. So exactly the same line as before. Okay, that line 12 hasn't changed on this next slide. I've only added this extra function up here inside the class declaration. So that G is now being called there and returning 4. Quiz time for you guys. How do I call for G defined on line 12? How do I call it? How do I modify line 13 to make this version of G get called? And renaming the function G is not the answer. Yeah, it's colon, colon. Okay? It's not like that. So again, this is about scope resolution matters. No colon, colon G within class scope there, that version of G gets called. Colon, colon gets us out into the global scope, and that version of G gets called. Okay? Again, we covered most of that off in week 1. Finally, oh, we've got some readings. Okay. So, because I don't think of the time, I've got some options for you guys here. We can either push on into the next lecture, we can call it a day. What do people want to do? Call it a day? Yeah, okay, I'll see you guys on Thursday.